Alright, so what we're going to look at now is how temperature and pressure affect physical state changes, meaning they're changing from solid to liquid to gas, or vice versa. Okay? I wish I had enough time to do a lab on everything we cover in here, because there are labs you can do on almost every concept we do in here, but you know what, you run out of time. You don't have enough time to do every possible lab we can do. And there are some pretty neat labs where you can actually see the results of the behavior we're going to look at today. We just can't cover everything. So some things you gotta be able to just use your head to kind of imagine these things happening, I guess. Okay, I wish I had time to go do more of it. I try to do demonstrations as much as possible. I try to do as many labs as we can, but after a while you run out of time to do everything we could possibly do. All right. What I want to do now is to look at how physical state changes with temperature and pressure. So what I need is I want to use a graph to illustrate the behavior, and this is the first quadrant of a Cartesian plane. Almost everything we do in chemistry will be on a first quadrant of a Cartesian plane. Now this is not a formal graph. We have lab work that you would do in here where you're required to do a formal graph. And in a formal graph you'd have a set of dots on here to represent where the data goes, and we'd have a best fit line or curve and that sort of thing. This is an illustration using a graph form. It shows you the behavior in general. And in fact, this is a very general behavior. So I want to put changes in temperature on the horizontal axis, the x-axis. And I want to put changes in pressure on the vertical axis. Now it's important to know that every substance has different temperatures at which it changes from solid to liquid to gas, or from gas to liquid to solid. So this representation here isn't specific to any particular substance. It's specific, or it's general, to show the pattern of almost all substances. And I say almost all importantly because there is a particular substance we're going to look at next that doesn't behave quite this way. All right? And we're only looking in general at solid, liquid, and gas phase changes because there are other phases. Water, for example, if you're really getting into the behavior of water, has like at least 5 different physical solid phases. Okay, but we don't get into that as deeply in high school as you might in other places. If you were involved in engineering, you might need to know that when you get into college or something. But right now, we're just kind of staying fairly general. And most everything we do in high school chemistry is going to be pretty general. Now, if the pressure is low enough, this is something you probably need to write this down because it's really important. If the pressure is low enough, if the pressure is low enough, there's no liquid phase at all. If the pressure is low enough, liquid phases don't exist. Okay, if the pressure is low enough, liquid phases don't exist. For example, in space, there is no liquid water. Okay? There's solid water, ice. There's gas, steam, although it's not hot. It's just the pressure's different. If, for instance, you were unlucky enough to be thrown out the door of the space shuttle without a spacesuit on, your blood would boil. It'd be really cold, but your blood would boil. Now, if you happen to be on the backside of the Earth from the sun, your blood would probably freeze. Okay, but your blood can't stay in the liquid phase in space because it's mostly water. Okay, the planet, or used to be a planet, they don't call it a planet anymore. Pluto. It has a carbon dioxide atmosphere around half of its solar year. When I say solar year, the time it takes for Pluto to go around the sun is thousands of years. And so it has an egg-shaped or elliptical orbit around the sun. When it's closer to the sun, the carbon dioxide that's on Pluto sublimates, becomes a gas, and Pluto has an atmosphere. When it's further away from the sun and it gets colder, the carbon dioxide freezes. Okay, so it's no longer an atmosphere anymore. It's part of the surface. So everything has this low pressure range where you can't have a liquid. And if we were to compare pressure and temperature, the point at which it changes from solid to gas. Okay, we're looking at where any substance is going to be changing from solid to gas, comparing the pressure and temperature which it happens. We're going to get a straight line in the beginning for that. That's kind of a straight line. Okay, so what kind of relationship do you call it when you have a straight line with a positive slope? The direct relationship between two variables, right? Okay, so as you change from as you increase the temperature, as you increase the pressure, if we were actually graphing where the phase change occurs, we get a straight line with a positive slope. So that's a direct relationship. So what I have over here on this side is solid phase for whatever substance. This could be iron, or it could be carbon dioxide, anything. It generally behaves in this way. And what's over here is a gas. Now, once the pressure gets great enough, then anything can be a gas, can be a liquid in liquid form if you have the temperature and pressure right. Carbon dioxide in this room can't exist as a liquid. Okay, if you can go to the grocery store. Well, you can't, but your parents can. Go to the grocery store and buy dry ice, and that's just solid carbon dioxide.
Why can't we?
Because people under 21 can't buy carbon dioxide. Can't buy dry ice. Okay, so you go to the grocery store and you buy some dry ice, and it doesn't melt. It goes through what's called sublimation. It changes from solid straight to gas. So for carbon dioxide, it gets right in this range. It goes straight from solid to gas. Okay? However, if we take carbon dioxide and put it in a big tanker truck and put it under a lot of pressure, we can get liquid carbon dioxide. And if you look at some of those trucks running up down the highway, those tanker trucks, you'll see on the side of it, it says liquid carbon dioxide. Okay? Well, that's because it's under pressure. Those are highly pressurized trucks to keep it in the liquid state. So, but if we get the pressure high enough, as we increase the temperature then, we can go from solid to liquid. And it's still going to be a straight line with a positive slope. So there's a direct relationship, again, between the solid phase and the liquid phase. It's not straight up. It's leaning slightly to the right, so it has a positive slope. See, it's not perfectly straight up and down. I'm leaning it to the right a little bit. Leaning it over that way. Now, I don't know if you've learned this yet in your math classes, algebra classes, or geometry classes, but curves can also have a slope. Okay, you know that already. Okay, and that's really looking at the tangent to a curve. I don't know if you know what that is or not, but the boundary between liquid and gas, as you increase the pressure and temperature, if we were to plot where things change from liquid to gas, where on this graph things change from liquid to gas, we're going to get a curve that has a positive slope as well. That means it can't go downhill. If it's going to be a positive slope, it's got to be going uphill all the time. But it's a curve, but it's going to start by going like this, but it's going to continue to curve upwards the whole time. Okay? So that's a curve with a positive slope. It's always heading uphill. Does that make sense when I say it's always heading uphill? Do you understand what I'm trying to say? Yeah. Okay? So as you compare the temperature and pressure at which this substance, any substance, changes from liquid to gas, we'd have a bunch of dots along here, and we'd have a best fit curve that would show that pattern. That makes sense to you? All right. So this is what this is showing. This is just showing the best fit lines and curves for this behavior we're looking at. So right here, if I get the pressure and temperature just right, so I take some carbon dioxide and I put it in a container, and I take some dry ice, which is solid carbon dioxide, and I increase the pressure and temperature to get it just at this point right here. I can have all three phases of carbon dioxide at the same time. It can be solid, liquid, and gas at the same time. Okay. Now you know water. If I leave a cube of ice cube out here on the lab table, it's going to melt. I'll have both solid and liquid water at the same time, but I don't have gas water at the same time. But if I put it under, if I reduce the pressure enough, I put the ice cube in a container and reduce the pressure, take out the air, enough air until the pressure is just right, I can have solid water as an ice cube, I can have liquid water as liquid water, and I can have steam all at the same time. It doesn't have to be steam at 100 degrees C if the pressure is lower. The more you lower the pressure, the lower the boiling temperature of water becomes. So if you go to Denver, Colorado, is that higher or lower than Spartanburg, South Carolina? Much higher. So the pressure is higher or lower? Now the pressure is lower. The higher you go, the pressure is lower. Okay? So if you're at sea level, that's 1 atmosphere. In space, that's 0. And the atmosphere, as you go up, as you go towards space, gets lower and lower and lower, closer to 0. Okay? All right. So if we're higher, the pressure is lower, and water boils at a lower temperature in Denver, Colorado. Okay? That's why they have special things on the boxes. When you cook things, you've got to change some of the conditions for cooking whenever you're in Denver, Colorado, because it cooks differently, because water boils at a different temperature in Denver, Colorado. Now there's a point, and so at this point here where I can have all 3 physical states at one time, this is called the triple point. It's the balance between temperature and pressure such that all 3 physical states can exist at the same time. For every substance, there's a point at which you can increase the temperature. So I'm showing you what's happening when I increase the temperature here. You can increase the temperature to a point where no matter what pressure you put it under, it still will never become a liquid. So down here, as long as the temperature is back this way, if I increase the pressure, I'm going to make it go from gas to liquid. But there's a point at which the temperature becomes so high that no matter what pressure you put it under, it's not going to be a liquid. And that point at which you can no longer make something be a liquid, no matter how much pressure you put it under, that point is called the critical point. So a critical point is the temperature above which a substance cannot be a liquid no matter how much pressure you put it under. So past this point here, there is no more liquid. Now my line kind of leaned back, but it should be a straight line going up. Okay? And this region up here, when we have a substance past that temperature at which it can't become a liquid, that substance then is called a supercritical fluid. Okay? Supercritical fluid. Now just to be clear, a fluid is anything that can flow. Alright? So that includes both gases and liquids. Alright? Do you understand that both gases and liquids can flow?